What is going on, everyone? Welcome back to another video. Today we are going to be linking two ANSYS analysis systems, steady state thermal and static structural, in order to analyze how a panel will warp due to thermal stresses. Let's get into it. So the example I would like to give you guys today is about this electrical cabinet that is usually found in residential areas to distribute electrical power to the homes. And we can study the panels on this cabinet in a thermal structural analysis to see how the temperature difference on the inside of the cabinet and the outside of the cabinet will cause the panels of the cabinet to warp. This is known as a thermal structural analysis, where the stress and the strain on the structure is not due to mechanical loads, rather, it's due to the thermal loads that it is exposed to. So there are multiple ways that I could view this situation. One of the ways would be that I dimension a panel to be 1 meter by 1 meter by 6.35 millimeters, which is equal to a quarter inch. And we could say that the temperature on the inside of the cabinet maintains the inner wall of this panel to be 40 degrees Celsius. And the ambient temperature around the cabinet maintains the outer wall of the panel to be 22 degrees Celsius. Evidently, this is going to cause thermal conduction through the plate. And the governing equation for that is Fourier's law, which says that the total heat flux is equal to the negative of the thermal conductivity times the area times the temperature difference divided by the thickness of the plate. And I have two videos dedicated on the topic of thermal conduction, which analyze the thermal conduction through one solid plate and the thermal conduction through a composite plate, which is analogous to an electrical system with resistances. I will link those videos in the description below if you guys want to explore this topic a little more. However, I will show you guys quickly how to set up the thermal conduction of a plate in this video, because we do need the thermal loads in order to do the structural analysis on this panel for this analysis. And on top of these thermal loads, as indicated by the holes in the panel is going to be bolted to the structure of the cabinet. And we are not going to be showing bolted connections, but we are going to resolve these as fixed supports in ANSYS to make our lives a little bit easier. And I'll talk about why we do this as we go through the simulation. And we'll be able to do a quick results validation in order to see if the results that we are getting are fairly good. This is very important when we're using multiple analysis systems, that we analyze the results as we go through the simulation to make sure that the results from one section that we're going to be using as the input for another section are not wrong and there's no snowball effect of errors happening. So for the thermal analysis, we will be able to validate the results since we know how to calculate the total flux through the wall by plugging all the variables into Fourier's law. The thermal conductivity, 60.5 watts per meter Kelvin, given to us as the default thermal conductivity for structural steel and ANSYS. The area being the 1 meter squared of the plate, and the temperature difference, the 40 degrees on the inside minus the 22 degrees on the outside, divided by the thickness of the plate, which is equal to 0.00635 meters, which gives negative 171,500 watts approximately of total heat flux going across this wall. And due to this thermal stress, we'll be able to see how the panel of the cabinet is going to warp. So all of that being said, let's go ahead and jump into Workbench and get started on this simulation. Now with Workbench open, we can go ahead and get started on this analysis. In the middle here, we have our project schematic. This is where we are going to be building the simulation with the analysis systems that are available to us in the toolbox here. For this particular simulation, we are actually going to be using two analysis systems, and I'll show you guys how to link these two together. The first one is steady state thermal, so we can go ahead and grab steady state thermal and drag that into our project schematic. And the second analysis system that we're going to need is static structural. Now, we know that the loads that are going to cause deformation are thermal loads that are given to us as a solution in steady state thermal. So the solution for steady state thermal is an input for static structural. Therefore, if you go ahead and grab static structural and drag that to the solution of steady state thermal, and we can see by doing this, the two analysis systems are sharing a lot of information. The first tab being the engineering data tab, this shares all the materials that we are going to be using. The second one, it is sharing the geometry, because we're not going to be changing the geometry during the analysis. So the geometry is going to remain the same. And for model, the two analysis systems are going to share the same mesh, which makes sense because when we determine a solution for the temperature at all the different nodes and elements, it's going to use this information to then calculate the stresses and strains at these locations as well. And as I mentioned before, the solution to steady state thermal, which is going to be anything temperature related, is going to share this as an input to the setup of static structural. So then we can then calculate what the structural deformation is going to be. So now that we know how these two analysis systems are going to be sharing their information between them, we can go ahead and start initializing the simulation. First things first would be to take a look at the materials that are available to us. So if we go ahead and double click on engineering data, this will open up a new tab in Workbench. So we have our project tab. This returns us back to our project schematic, and we have the engineering data tab. And I would like to note in the engineering data tab is indicated by A2 and B2, and this corresponds to our two analysis systems, A2 and B2. So this means that A2 and B2 are sharing the information that we are going to gather here. So by default in ANSYS, ANSYS always runs structural steel, and this is going to be the material that we are going to use for this simulation because it does have all of the properties we could ever ask for. However, if you want to add a different material, this is very easy to do. You go ahead and press on engineering data sources, and this opens up all of the material and different material libraries that are available in ANSYS. So if we go ahead and just pressed on one of the material libraries, say general materials, in the middle here, this would open up all the materials in this library. And if we pressed on, say, titanium alloy, this would open up in the third window down here, all of the material properties that are by default in ANSYS for this material. And say we wanted to add titanium alloy to our project for whatever reason, this is done by pressing on the big plus right here. And we can see that there's a little book that appears beside the plus, and this means that it has been added to our project. So that is how to add a material to your project, just so you guys know. For this analysis, I'm going to stick to structural steel, but I wanted to show you guys how to add different materials so that you could perform this simulation for your specific case. So having verified the materials and adding materials that we needed, we can go ahead and go back to our project by pressing on the project tab up here. And now that we have a check mark beside material, we did before, because again, by default, ANSYS has us running structural steel, so material is never an issue. So now that we are done with materials, we can go ahead and double click on the geometry to launch SpaceClaim. So double click on geometry, and in the bottom left corner here, it says starting SpaceClaim, so I'll wait for that to load. Now with SpaceClaim open, we can go ahead and start building the geometry for this analysis. By default, ANSYS has us sketching on the ZX plane. I prefer to sketch on the YX plane. It just makes it easier for initializations later on. So I'm going to go ahead and press on End Sketch Editing. And then to re-enter sketch mode, I'm going to press on the big pencil crayon up here. And I'm going to choose the plane that I want to sketch on. I'm going to press on the Z axis to make it normal to the screen. And now I'm going to build my geometry for this analysis. It's a very simple geometry. We are building a square, a 1x1 meter square that has a thickness of 1/4 inch or 6.35 millimeters. So to do this, I'm going to go ahead and choose my rectangle command up here in the create section of the toolbar. And I'm going to choose the origin to start creating this rectangle. I'm going to drag out the rectangle. And we can see that there's two dimensioning lines that appear. I'm going to enter the dimensions that I just mentioned. So 1 meter or 1,000 millimeters. By pressing on tab, it will go to the next dimension, and I will insert this dimension as 1,000 millimeters. Press enter, and then this creates our square. Now that we are done with the sketch for the plate, I'm going to go ahead and press on End Sketch Editing. And with the sketch that we created of the square, this is going to create a solid surface. To make this a 3D shape, I'm going to go ahead and use the pull command from the edit section in my toolbar. And I'm going to press on the coordinate axis so I can see it a little better. I'm going to grab the surface with the pull command by holding left click, and I'm going to insert my dimension as I'm holding left click to be 6.35 millimeters, again, representing 1/4 inch. And as you can see, we now have a 3D solid from the 2D surface that we used to have. Next up, I'm going to create some holes at the corner of my panel, and these are going to represent the bolt holes that hold the panel to the structural frame of my cabinet. To do this, I'm going to go ahead and re-enter sketch mode by choosing the pencil crayon up here. And I'm going to choose the surface of my panel. I'm going to take the circle command and input a circle somewhere on my panel. I'm going to dimension the circle to be 25.4 millimeters. And by using the dimensioning command, I'm going to go ahead and specify this circle to be 50 millimeters away from each side. So I'm with the dimensioning command, I'm going to grab the center of my circle, grab the edge of my panel, and drag the dimension out to the side and left click again. As you can see right now, it's 113 millimeters. So to change this, I'm just going to click on the 113 millimeters and change this to 50. Press enter, and you can see that the circle has now moved to 50 millimeters away from the edge of my panel. So I'm going to go ahead and redimension the side here to be 50 millimeters as well. And I'm going to do the exact same thing at each corner of my panel. And there you have it. So now that I'm done the sketch for the bolt holes on this panel, I can go ahead and press on End Sketch Editing. And then by using the pull command, I can cut out these sketches to create the holes. So choose the pull command, and using the control key on my keyboard, I'm going to hold it and press on each of these sketches to select all 4 of my circles, like so. And then I'm going to drag the circles backwards through my plate. And as you can see, if I let go, this has now created a hole in my plate representing the bolt holes. So now with the holes created in my panel, this completes the geometry that I need to set up this simulation. So now we can go ahead and move on to the mechanical part of this simulation setup in order to mesh this geometry and set up all the boundary conditions and actually run the simulation. So I'm going to exit SpaceClaim by clicking on the big X. I'm going to return back to Workbench, and now we can see that we have a check mark beside geometry, so that is good to go. And we can see that it has been shared from the steady state thermal where we built the geometry to the static structural tab as well. So now we can move on to the meshing stage. So let's double click on model, and in the bottom left corner here, it says starting mechanical. So I'll wait for that to load. So now with mechanical loaded, we can go ahead and start building the mesh. To build a mesh, I'm going to go ahead and right click on the mesh in the project tree here, and I'm going to press on generate mesh. And this is by default going to generate the default mesh that ANSYS creates without any user input or guidance. And as we can see, the elements that have been created are very, very coarse and not very orthogonal. As we get towards the holes, it doesn't really know what to do because the elements are way too big. So we can go ahead and add a body sizing. To do this, I'm going to go ahead and right click on mesh and go to insert and press on sizing. The yellow fields down here means that ANSYS is waiting for user input to properly handle this sizing. So it's missing out on the geometry, and it wants us to specify the definition for this sizing. So let's start with the geometry. I'm going to go ahead and choose my body selector command up here in the toolbar. I'm going to press on the geometry that we have, and I'm going to press on no selection, press on the apply button that appears. So now one geometry or one body has been added to the geometry for this sizing. Next up, for the definition, I'm going to specify the element size. And we can see that by default, the element sizes were 0.07049 meters. However, as we saw, this was way too big. So I'm going to specify the elements to be 0.01 meters instead. So now we can see we have a lightning bolt beside mesh. So the mesh has to be regenerated in order for it to incorporate the specifications for the sizing that we wanted. So to regenerate the mesh, I'm going to go ahead and press on or right click on mesh and press on generate mesh again. And now we can see in the viewing window here that the mesh that has been created is a lot more refined. The elements are a lot more orthogonal, and specifically at the holes, yes, there are a few elements that are a little skewed, but overall it has a better time at meshing around the holes that we've created. And we can go ahead and check the quality of the mesh if we wanted to do that. So if we press on the plus beside quality, and where it says mesh metric, we press on element quality. This opens up a bar graph in the bottom window here, and we can see some of the stats about the elements within our mesh. We can see by clicking on the column of this bar graph that most of the elements fall in the higher range towards 90%, where 1 is equal to perfect orthogonality. And by pressing on the column near the lower end of this scale at 53%, if we press on that, we can see that there are only a couple elements that are very, very skewed. However, overall, our mesh has fairly good quality, and a lot of the elements are very orthogonal, and there's not many that are, and if they are, they're not very skewed. So that is fairly good and should not be a problem for our analysis. With the mesh created, we can go ahead and add the boundary conditions that we specified in the problem statement. And these boundary conditions were the inside and the outside temperature of the cabinet. So to do this, I'm going to go ahead and right click on steady state thermal. I'm going to press on insert and I'm going to press on temperature. And you could insert different boundary conditions if you had a different boundary condition to specify. But for this analysis, I'm only going to be specifying the temperature on the inside and outside of the wall. So I'm going to insert a temperature. We can see that for the details of temperature, we need to specify a geometry. So to do this, I'm going to choose the face selector command, and I'm going to choose the left face of my panel, and I'm going to go ahead and press on apply. So now one face has been added for this temperature, and by default, ANSYS has 22 degrees Celsius or room temperature as the definition of this temperature. In the problem statement, I specified that the outside temperature or the ambient temperature would keep this panel at 22 degrees Celsius on the outside. So I'll leave this as 22. But on the inside, we wanted to specify that the electrical components are going to hold the panel at 40 degrees Celsius. So to do this, I'm going to insert another temperature by right-clicking on steady state thermal, going to insert and pressing on temperature. Using the face selector command again, I'm going to rotate to the other side of this geometry and choose the inner face. I'm going to press on apply on temperature. And for the magnitude of the temperature, I'm going to press on the 22 and insert 40. And so now a boundary condition of 40 degrees has been added to the other side of my panel. And that will be it for all the boundary conditions for steady state thermal. Now we can add a few solutions in order to help with the results validation as we go through this analysis. So in solution here, I'm going to right click on solution, go to insert. I'm going to go to thermal and insert temperature. And what this is going to do is be able to show me the contours of the temperature once it calculates it at all the nodes and different elements in my mesh. So that should be it for the setup of the steady state thermal part of this analysis. So now we're ready to solve this part of the analysis in order to get the solution for the temperature loads so that we could use it as an input for static structural. So I'm going to solve it by right-clicking on steady state thermal and pressing on solve. And if we press on the solution information here, we have the solver output and it will start writing some stuff out to the solver output. And we can see that since this analysis is very, very simple and the geometry is simple and the mesh is very simple and very orthogonal, it took no time to write out all of the information and calculations that it needed. So we can go ahead and view the results that we got. If I press on temperature, we can view the temperature gradient through the wall. To start with our results validation based on this steady state thermal analysis, we can see that our boundary conditions are being respected. From the color bar here, we see that the lowest temperature is 22 degrees Celsius, which represents the temperature on the outer side of the panel. And our highest temperature is 40 degrees Celsius, which represents the highest temperature boundary condition on the inside of the panel. The other thing that we can do for results validation at this point is, as I specified in the slides, using the Fourier's law, we were able to calculate the total heat flux that was passed through this wall, which was equal to approximately 171,500 watts. And to verify this information in ANSYS, we can go ahead and select both our temperatures here, temperature 1 and temperature 2, and drag this into our solution. And as you can see, we have two reaction probes that have been created. There's a little lightning bolt, so this means that the solution has to be resolved. So to do this, I'm going to right-click on solution and press on evaluate all results. And this is going to evaluate the reaction probes based on the solution for the temperature that steady state thermal previously calculated. And if I press on reaction probe, we can see that this is calculating the reaction on the outer wall. And we can see that the reaction probe has a unit of watts and has a magnitude of negative 171,150, representing the total heat flux that passed through this wall. And if we press on reaction probe 2, we can see that we have the same magnitude of heat flux passing through this plane of the panel as well, which makes sense because the heat flux through the whole panel needs to stay the same. So now that we've done the results validation and concluded that the results that we have obtained are fairly good and are representative of the boundary conditions that we put into place, we can go ahead and analyze the strain and stress this is putting on the structure. So if we go ahead and go down to static structural in imported loads, if we press the plus on imported loads, we can see that static structural is importing the imported body temperature, which is the solution that it calculated during steady state thermal. However, if we were just to solve the information as is, we would get an error in ANSYS because we need to bound this simulation. As of right now, this panel is just kind of floating in free space. And so if we were to only apply a thermal load, static structural wouldn't really know what to do with this. We need to somehow bound this geometry in space so it just doesn't fly off. And this is where the holes that I created in the panel come into play. I'm going to go ahead and add a fixed support for the bolted connections, acting as if it was bolted to the structure of the cabinet. Therefore, the panel would be restrained at the four corners, but be able to warp in any direction that it needed in reaction to the thermal loading on it. So to add a fixed support, I'm going to go ahead and right click on static structural. I'm going to go to insert and press on fixed support. We can see that we need to add a geometry force fixed support. So I'm going to go ahead and use the face selector command and select the interface of all of these bolted connections. Holding control, I'm going to choose the interface here of my bolted connection. Holding control, I'm going to choose this one. I'm going to go up to these two, still holding control and still holding control. I'm going to choose this. So we can see that we have four faces that have been highlighted that represent where my panel is going to be bolted. And we can apply this to the geometry of my fixed support. So we can see that four faces have been added to the geometry of the fixed support. So now that we've bound this geometry in space, the panel can now react how it wants to the thermal stresses without it flying in some random direction. And like we did for steady state thermal, we need to add some solutions to static structural in order to see the results that we want to get. So I'm going to right click on solution, I'm going to go to insert, press on deformation and press on total. And this is going to allow us to see the total deformation of the panel. And I'm also going to do this, go to right click on solution, go to insert and press on stress and go to equivalent von Mises. And this is going to show us the stress of the panel as well. And this is going to be particularly important in order to see the stress at my bolted connections. Now that we've told ANSYS what results we want to see and we have our boundary conditions put into place and our loads imported, we can go ahead and solve the analysis in static structural. So I'm going to go ahead and right click on static structural and press on solve. Now that ANSYS has completed its calculations, we can go ahead and analyze the solution that we've achieved. If we press on total deformation and we rotate this panel a little bit, we can see that the panel is in fact warping due to the thermal stresses that have been acting upon it, causing some sort of bulging in the center of the panel. And this makes sense because we have it connected at its four corners or fixed at its four corners. Therefore, it has the most mobility farthest away from these bolted connections being the center of the panel. And we can see that it is respecting boundary conditions because we see that the dark blue represents a total deformation of 0. And this makes sense because since we fixed the corners, we would not expect it to deform much, if at all, at these bolted connections. So this is a fairly good result. If we go ahead and press on equivalent stress to see the stress, it tells us a similar story. Because the middle of the panel has the most movement in it, it is not under a lot of stress. Since the bolts are retaining the panel from moving at the four corners. This is causing there to be a lot of stress at these corners, and therefore we see the maximum stress at the bolted connections. So unexpected result. So overall, I think this was a fairly good analysis to learn how to do a thermal structural simulation in ANSYS. Evidently, you can go ahead and add some more thermal restraints to your panel and add more mechanical loading or restrictions to your panel in order to perform the desired simulation that you want. And one more thing that I forgot to mention, there is an animation that has been created for the solution that we've achieved here. So if I go ahead and press on total deformation and rotate this panel so we can see more of a side view of it and press on the play button on the animation, we can see that the panel is bulging due to the thermal loads acting on it. And we can see that the corners of the panel where I have my bolted connections are remaining still. And evidently my panel, if I press on stop here, evidently it looks like my panel is bulging a lot, but I rest assure you that it's not actually warping or bulging by that much. We can see here that the maximum warpage is equal to about 2.4 millimeters. If I go ahead and press on results here, we can see that the solution or the display of the solution is being auto scaled upwards by a factor of 29. So if I go ahead and press on undeformed, this is the true scale of my deformation based on the size of my panel, and we can barely see any deformation. So it's useful if we go to results and where it says in the display section here, we scale the results that we've obtained in order for easier viewing of what's going on with our panel due to the loads and battery conditions that we've set upon it. And with all that being said, I think the solution that we've obtained here is fairly good. And I hope you guys were able to learn a little bit of how to set up a thermal structural analysis by using this panel of the electrical cabinet as an example. So that will be it for this tutorial. Don't forget to like the video if you guys thought it was helpful and subscribe for more engineering content.